practical reason, because I want to be able to see precisely the things you see while you are watching my talk. Because as a person who gives the talk, I cannot see my slides in the same way you do. So just for my personal comfort. I hope it's not disturbing for you.
Not at all. You've got two screens in front of you then, have you?
Yeah.
What are you doing, Scott?
Okay, so we're very pleased indeed to welcome Victoria from Caen in Normandy, France, who's going to talk about unexpected applications of homotopical algebra to knot theory. I can read as well as you can.
So hello to everybody. Thank you very much, Roger, for this opportunity to talk in front of you and to see you all, even though it's only virtually, unfortunately. So my topic for today is unexpected applications of homotopical algebra to knot theory. The most unexpected word in this title is probably the first word, unexpected. So when you see the title, you might wonder what can be unusual about bringing together homotopical algebra and knot theory. They can be put together in so many natural ways. So the connections I will present today are probably not the ones you would naturally think of. So now how the talk will be organized. And in the first part of this talk, I'll give a crash course on rakes, quandles, and their homology, and I will explain why these objects are very useful for creating tools for knot theory. The interesting thing about these objects is that they are very easy to define. So these objects and their homology theories. In a algebraic way, you can do everything in 2 lines. But then there comes the difficult part of the story. These things are almost impossible to compute. There are only a couple of families of rakes and quandles for which we can explicitly compute the entire homology theory. And now this is where the homotopy theory will come in. So I will explain that at least in some cases, one can make the entire computations of rake homology theory using homotopical methods. And so the particular example I will work with today will be the one of permutation rakes, which are the ones represented by a very simple formula. And I will explain that to understand them, you need to understand a very, very simple thing, a space which is built out of a permutation phi, which defines your rake. And this space is very, very simple. From this picture, I think you can guess how it works. And from topologically speaking, this space will contain just some lines, 1 line for each infinite orbit, and some circles, 1 circle for each finite orbit. So topologically speaking, it's something very, very simple. And now, the honest title of my work is of this talk is the homology of permutation rakes. This is really the new result I'm presenting today, and it is based on our recent work with Markus Schimmick from Norway. So let me start up. Well, since many of you in this audience know much more than I do about rakes and quandles and their homology, you will not need the first introductory part of the talk, and that is why I suggest that you can maybe take it as a challenge and try to compute by yourself the full homology of the permutation rake for a given permutation phi. Personally, I know how to do it in using exclusively combinatorial methods, but this is not beautiful at all. So maybe some of you will come up with with an elegant argument. So this is why we thought of applying this homotopical techniques to this object. So now I'm returning to those of you who are maybe less familiar with self-distributive things. So the ideas come from the following thing. Try to think of the Wirth representation of the fundamental group of the complement of a knot or of a braid of your favorite object. This is something you all know very well, and it uses the only thing it uses is the conjugation operation in your group. And so when you replace this conjugation by an abstract binary operation triangle on a set S, you naturally come to the idea of the colorings of braid or knot diagrams. So by the colorings, we mean the following thing. We take a diagram and we color all the arcs of this diagram by some elements of your set. And around each crossing, you impose a coloring rule saying that whenever you go under a strand which is colored by B, so your original color A becomes a triangle B. So this works for positive crossings, and for negative crossings, you have a similar rule. You should just go in the opposite direction. So this is completely inspired by this Wirth representation of the fundamental groups of the complements of your objects. Now you want these colorings to be topologically meaningful. For this, you need to check that they are that the Reidemeister rules, Reidemeister moves preserve them. If you look at the Reidemeister 3 move, for example, you see that these coloring rules above allow me to extend uniquely all colors on the left to the right. And you see that on the right, you get the same color on the two lower strands and potentially different colors on the higher strands. So you need to impose these two higher colors, which I showed in blue, to be the same. And if you look carefully at these expressions, you recognize the self-distributivity relation. Maybe you're more used to seeing this self-distributivity, this distributivity when you have two operations. For example, the multiplication of real numbers is distributive with respect to the sum. But here we need only one operation. This is why we are talking about self-distributivity. In a similar way, you can translate the Reidemeister 2 move to this algebraic language. It will tell you that all the right translations should be bijective. And the Reidemeister 1 move is translated by saying that all elements should be idempotent with respect to your new operation. So we're talking about a shelf when we have a set with a binary operation satisfying only this self-distributivity axiom. We're talking about a rake when we have the two first axioms, and we're talking about a quandle when we have these three axioms. All these words come from quite interesting historical reasons, but I will not dwell on it today. So now, what do these colorings give us precisely? So if you take a braid, if you take on n strands and you choose some n colors on the left, so these coloring rules can be used to propagate your colors in a unique way to the right. And in this way, you can define an action of a braid on an n tuple of elements of your set S. So if you have only a shelf, it will be an action of the positive braid monoid. If you have a rake, which allow you also to Reidemeister 2 move, you'll have an action of the whole braid group on the n tuples of elements of S. Now, the Reidemeister 1 move does not make much sense for braids, but here, if we are talking about the actions, it gives you something quite funny. It gives you a copy of elements which the action is trivial. These elements are just the tuples where all the elements are the same. So it means that if you are working with the representations, you have a bunch of identical, a bunch of trivial representations, and you will be able to reuse things. And so this offers you a beautiful setting for looking together at very different constructions in braid theory. For example, if your underlying set is just a set with an action of Laurent polynomials in one variable, you can define a binary operation by this linear, by this formula. It's just a linear combination of A and B, and what you get is an Alexander quandle. If you work with the corresponding colorants, you'll get the Barrow representation. And you get the reduced Barrow representations if you mod out the copies of the trivial representation I was talking about. If you start with a group and take as your binary operation the conjugation, you will get a quandle which is called a conjugation quandle. And from it, you can extract, for example, the artin action of the braid group on the free group. So it's also something very basic in braid theory. If you play with the first definition of the Alexander quandle a little bit and twist it in a certain way, you can actually get the Lorentz-Kramer-Bigelow representation of braid groups out of it. But even if you start with very simple objects like you take all the integers, and as the operation you take A times B equal A plus 1, you'll get a rank, which is actually the free rank on one generator. And from it, you also extract some very simple but still non-trivial topological information, which is the length of the words in your braid group. Or if you modify this example a little bit, you will get the linking numbers for different strands. And if you take the free shelf generated by one element, you get actually a very complicated object. And this is interesting because it's very different from a free group. A free group on one element is something you understand very well. A free shelf on one generator is something very hard to understand. And from the understanding of this object, Patrick Dernat was able to deduce his order on the braid group. And you can definitely play the same game with knots. So you have the same colorings with the same coloring rule. For example, to color this diagram of the trefoil knot, you get 3 colors, which will be related by 3 relations. And since if you have a quandle, you have automatically the compatibility with the 3 random master moves, you can just compute the number of colorings of a diagram by a given quandle. It will give you a number which is not invariant. A very simple example is the numbers modulo 3 with this very simple operation. On the level of colorings, it will mean that around a crossing, either all colors are the same or all colors are different. And you actually give the famous idea of Fox colorings, which is the easiest way to distinguish the trefoil knot from the unknot. Now, what is good about this invariance? First of all, there is a huge number of racks and quandles of small size in nature, and given one, it's technically quite easy to compute these colorings. So you have an easy invariant. But on the other hand, it will be very powerful because of the following thing. Counting these colorings is the same thing as counting the morphisms, quandle morphisms from the fundamental quandle of your knot to the given quandle S. So the fundamental quandle of a knot is given by presentation and relations, and you can see it from the picture. You get one generator for each arc and one relation around each crossing. You just give the generators and relations, and it gives you a presentation of your quandle. And the fundamental theorem about this, which belongs to GSM and wave, is that it is a weak universal knot invariant, which means that it can distinguish everything except for couples of a knot and the same knot with and the mirror image of the same knot with the reversed orientation. So in particular, these invariants cannot distinguish a trifle node and its mirror image. Having this in mind, we can ask ourselves how we can strengthen this invariant. For this, we can just try to summarize what we have done before. We have seen that if you apply a rider master move to a diagram, it will change the coloring of your diagram only locally, only in the ball where your rider master move is being applied. Now, outside the ball, nothing changes. So it means that you have a very explicit bijection between two coloring sets. And if you have a bijection between two sets, certainly the two sets have the same size. So it is the simplest thing you can extract from a bijection. This is how counting invariants work. Now you can ask yourself whether you can have something more subtle. We would like to associate some mathematical objects, a number, for example, for each coloring, such that when this local rider master move happens, the number you computed out of your original coloring is the same as the number computed from your final coloring. If this condition holds, then you can look at multisets of your numbers computed for all the colorings, and you will have the same multisets. For this to work, you need these objects you associate to a coloring to respect the three rider master moves. And so a way to do it can be taken from physical inspirations. So you can consider the so-called state sums. So you have a diagram of your knot colored by a quandle in the way we discussed before, and you take each crossing and you look at the colors around each crossing. There are two particular colors which are of interest to me, A and B, and I would like to have some map phi which I would be able to evaluate on these two colors. So it's a map which can evaluate which can be evaluated on a couple of elements of your set S, and which takes the values in an abelian group, let's say integers modulo m. And so you have this evaluation on these two colors, and you take it with the sign, which is the sign of your crossing. Now you can ask yourself whether this thing can be compatible with the rider master moves. So for the rider master 3 move, you have 3 crossings, so you need to consider the sum of 3 evaluations on the left and on the right, which can simplify a little bit, so and give you a kind of 4-term relation. For the rider master 1 move, you will have a 1-term relation, like here, and the rider master move number 2 comes for free because of the plus-minus choice here. If you have a map phi which satisfies these 2 conditions, then you can use this state sum type formula to produce some numbers modulo m, and the multiset of such numbers, 1 for each coloring, will give you a quandle cocycle invariant. So it's certainly an enrichment of the construction we had before. The zero map satisfies the 2 conditions we needed, and so if you take the zero map, all the omegas will be 0. So you just have a multiset of zeros, which means that you're just counting your colorings. But these invariants are actually stronger than the counting invariants, for example, since they can distinguish the 2 trifle nodes. And there were quite a lot of actual computations on it, which can lead to some people to conjecturing that if you consider all finite quandle cocycle invariants, you will be able to distinguish all nodes. As far as I remember, in the work of Clark and Saito, they used just something like not more than 20 quandles with corresponding cocycles to distinguish the nodes up to I think 12 crossings or something like this. So which is really, really powerful. One more good thing about this is that all these coloring ideas can be generalized to having two n-dimensional nodes, which are noted in the space of dimension n+2. So for this, you'll also have to consider these multiple crossing points, and you'll have you'll need to have some maps which you will be able to evaluate on the input colors. So you need some maps phi, which take n+1 inputs in S, and have one output in the integers modular M. And so what we would like to have is having try to organize the conditions we need for the map phi to be topologically reasonable in a proper way. And the natural way would be having a cohomology theory. And we would like to have the following property. Whenever we have a cocycle for this cohomology theory, these types of Boltzmann weights should give us invariance for n-dimensional nodes. And whenever we have a coboundary, this invariant should not give us more information than just counting the colorings. And the good thing is that such a theory has been constructed, and you can write the construction explicitly just in 2 lines. So you start with a shelf and an abelian group, which will play the role of coefficients. Usually we take integers or integers modulo M, and you consider the cochain complex. In degree K, you'll just take all the maps from the Kth power of your set S to your group X, to the coefficient group X. And the differentials work as follows. You take a map F, which can take n entries, which can take, k entries, and you need to produce a map which takes k+1 entries. To do this, well, you can do a number of things. You can, for example, throw away one of the entries, so it reduces the number of entries, which is nice. Or you can do something more involved. You can throw away an element and at the same time make it act on all the preceding elements just by this formula. And what we are taking is a kind of a signed sum of all these expressions. And the nice thing is that if you apply this map D twice, you'll get 0, so that you rarely have a cochain complex. And so you can take the kernels of these maps and divide by the images to take, and it will give you what is called direct cohomology of a shelf. If your shelf is something better, for example, a quandle, then you can restrict yourself to a subcomplex of the complex above by saying that you work only with the maps which are 0 as long as some neighboring elements coincide. So when you evaluate your map F on some k tuple containing some repeating entries, so you need your map F to be 0. So the quandle cohomology, the cohomology of the subcomplex. So that's the thing, and it gives you what you wanted. So if you come from knot theory, which is the case for most of you, for you it would be a source of knot invariance and also invariance of higher dimensional knots, as I explained before. This invariance will be powerful and easy to compute by a computer. If you come from algebra, you will also be interested in these complexes because they give you an important class of braided vector spaces, which are important in a classification of certain Hopf algebras. And in the second cohomology group also encodes what is called abelian extensions of Rex. So this is a very nice theory, but the problem with it is that, well, if you have this definition only, it's almost impossible to compute the cohomology of a given Rec. So as far as I'm informed, the only types of Recs and quandles for which these cohomology groups have been entirely computed are the trivial Recs, the free Recs and quandles, and the Alexander quandles of size p, of size some prime number p. So which is very, very restricted. Now I'll give you a couple of available tools just to give maybe more volume to this theory. So the first one is a topological realization. Starting from every shelf, you can construct an explicit topological space, which will be a CW complex, and it's called the Rec space or the classified space of your shelf. It's quite easy to construct. So in degree 0, you just take a point. In degree 1, you'll have an arrow for each element of your shelf. In degree 2, you'll have squares with the boundaries indicated like here, A, B, B, and A times B, and with the orientations like indicated in the picture. So these squares can be seen as the dual object to the crossings properly colored by the rules I explained. Now in degree 3, you'll add some cubes. Here I depicted the upper and the lower part of the cubes. So how do you color the edges of a cube? You start with the green colors at the bottom, A, B, and C. And then using these rules for coloring the squares, it uniquely propagates everywhere on the top and on the bottom sides. And if you want these two parts to be gluable, well, you need to see what happens on the boundary, and you see that the only place where gluing is not automatic is this one, where the labels were put in blue. And you will be able to glue these two halves even only if you have, once again, this subdistributivity condition. And a nice way to think about these cubes is the dual objects for your randomized 3 move. And this happens more generally. You can take a cube of dimension n, then orient it properly and color n edges of this cube as I showed here. And then if you have something subdistributive, then the rules for coloring the cells of lower dimension will allow you to color in a unique way this cube without any contradictions. And so that is how the n-dimensional cells are constructed. And the boundaries are the usual topological ones. For example, the boundary of a cube will consist of 6 squares with certainly with the induced colorings. And if you play with the formula defining the Rec cohomology a little bit, you'll see that this CW complex has the same cohomology as your Rec. This is very easy to obtain. And if you need, if you want to work with quantal cohomology, you'll just need to add some 3-dimensional cells with the boundary indicated like here. So this construction is very useful for example, understanding the algebraic structure of this cohomology. For example, you can say that, well, it's the cohomology of a ZW complex, so it will have a K product, which will certainly imply a K product on the Rec homology, which you can also do explicitly. but this is not very helpful in actually computing the homology. So on the theoretical sides, this complex is nice for explaining the relation between a rake and its associated group. The associated group is given by generators and relations. You take one generator for element of your set, and one relation for a couple of elements. You say that A times B is the same thing as B times a triangle B. So this is something which is very useful when you're studying a rake or a quandle algebraically. But if you think in terms of the rake space, so you can read this relation from a square which forms your cells of degree the cells of degree 2 of your CW complex. So A times B is the same thing as B times a triangle B. Which means that this group is actually just the fundamental group of your X space. So I will return to this connection slightly later, and now I'll just mention the only two cases I know where these Rex spaces have been completely understood. So for the trivial quandle, this Rex space is the loop space of a wedge sum of n spheres. And for the free recon n generators, this Rex space is a wedge sum of n circles. So these are very understandable objects, topologically speaking. That is why you can extract cohomology computations from these things. Now I'll talk slightly more about the associated group. So one of the remarks is that actually it is a part of an adjoint functor. So from a rake, you can construct a group using this definition. And on the other hand, at the beginning, I explained you that if you have a group and consider the conjugation operation on it, it gives you a quandle, and so in particular a rake. It is actually a pair of adjoint functors. And they can be very helpful if you're interested particularly in computing the cohomology of your quandle. So a very nice precise result of Garcia Iglesias and Rudman tells you the following thing. If you take a quandle which is finite and indecomposable, by decomposable I mean that if you consider all the right translations and the orbits of under all the right translations, you'll get only one orbit. So in this case, you can explicitly describe the second cohomology group of your with any coefficients x. It will be just a direct product of x and the set of group morphisms from a certain finite group to x. This finite group can be described very explicitly. I will not dwell on it, but the point is that everything reduces to the understanding of this group, and it can be done in practice by a computer relatively easily. So you get a very nice machinery for computing this second quandle cohomology, which is second rank cohomology, sorry, which is actually the most interesting part of the cohomology, because this is what is needed for rakes, for constructing invariants, or also for this homology classification thing. Now, in general, if you want to understand cohomology in higher dimensions, the only thing we can say is that there will be a map between the Haustian cohomology of this associated group and the rake cohomology of your quandle. And the existence of this map is very natural from these rake space ideas, because on the right you have the homology of your rake space. And on the left is just the fundamental group of this Rec space. So it's very natural to see some connection between the homologies of these two, and this can be done in a very explicit way. So this map can be constructed very explicitly. But once again, it can add some light. It can shed some light on the on these homologies, but in practice, it is not enough for actually computing them. And one more result which I would like to mention, a classical result, is that if you want to construct a direct cohomology of a rec, not only a shelf, and if you have some technical condition, then this cohomology is just a direct sum of some copies of X. And the number of the copies of X you should take is R power K, where K is the degree in which you are working, and R is the number of orbits of your rec. But once again, when I'm talking about the orbits, I'm talking I have in mind the orbits with respect to the action by right translations. So the only information encoded in these homologies is the number of orbits of your rec. Now the technical condition I need is the following thing. So you can consider the automorphisms of your rec generated by the right translations. And it will give you a group, which is the subgroup of all the automorphisms, and it is called the group of enamorphisms. So since your rec is finite, it will be a finite group, and you can look at its size. And so if its size is invertible in your abelian group X, where you're taking your coefficients, then you have this formula. So for knot theory, it's actually bad news, because it means that under this technical condition, quandle cosecant invariants are actually nothing more than coloring invariants plus some linking numbers. But there is some hope, and the hope is to get some interesting things when this technical condition fails. So typically you'll need either to take as coefficients the numbers the integers modulo p, or take, for example, integer coefficients and look at the p torsion of your homology, where p will be a prime divisor of the size of this group of inner automorphisms. And actually, this works. There are plenty examples of recs where there is some non-trivial p torsion, and this is what actually gives you the interesting invariants. So there are a couple of other important results for the general case, but they all allow some simplification in the calculation of the full rec or quandle cohomology, but actually they never actually lead to complete answers. Now I will move to the new part of this talk. So this idea to use the homotypical tools to compute this rec and quandle homologies goes back to my co-author, Marcus, who wrote a paper entitled "Quandle Homology is a Quillen cohomology," which is actually the essence of this paper. So it interprets quantum cohomology as a particular case of Quillen cohomology. So the applications he had in mind is using some general tool for this in the homotypical world, like having excision, isomorphism, or the Meyer-Vittori's exact sequences, to do some actual computations. So as for now, it remains a general framework, but as far as I know, no concrete computations have been extracted from it in the full generality. Now I'm moving to the particular example which we
Sorry to interrupt,
considered.
Victoria. Can we go back to that? Sorry, I wasn't concentrating. When you say, did you say what a Quillen cohomology is?
No.
No.
It's I'm far from being an expert from it, but these are the kind of homologies which you get in a very abstract setting by considering resolutions of your object by some kinds of free objects. So by some kinds of free simplicial objects. So in general, this is quite an abstract thing. You don't always understand what these free simplicial objects look like. But this will be, this is just to give a general framework. It will be, I think it will be more understandable on the particular example I will look at.
Okay.
So just to say that what quandle homology has some completely homotopical interpretation.
Okay. Yeah, sorry.
The message of this side. Now, thank you very much for the questions. So now the family of regs we are going to work with now are the permutation regs. So you take a set S, a permutation phi on it, and you say that A triangle B is phi of A. So it's very easy to check that this will be actually, this will be indeed a reg. And it's almost never a quandle. To beat a quandle, you need A triangle A to be equal to A. It means phi of A is A. So you can only take trivial permutations to get a quandle. So we are really working here in the framework of regs. Now our main result gives you the entire homology of these permutation regs. So the first comment is that we prefer to work with homology rather than cohomology, but it can be all translated to the cohomological language and the result will be identical because what the groups you have are all free abelian groups. Now, also, if you prefer, you can take the S coefficients just integers, if it's easier for you. And so the theorem said that in degree K, you will have just a bunch of copies of X, where X again is the group representing your coefficients. For example, take Z or Z modulo M. And the number of copies you take can be given by some recursive formula, which depends only on two numbers. So the first number is the number of orbits of your permutation, which is R. And the second number is the number of finite orbits among the orbits, which is RF for finite version of R. And that's it. So there are a lot of things you can say about it. So for example, if you have only finite orbits, this formula simplifies and you'll get the Betti numbers which you knew from the results on the previous slide. Another consequence of this result is that their homologies contain strictly more information than the associated groups in this case. So the associated group for a permutation reg like this will be the free abelian group on R generators, where I is once again the number of orbits. So this associated group sees only the number of orbits of your reg, whereas the reg homology sees two things: the number of orbits and the number of finite orbits. So it has it contains slightly slightly more information. This can be you can say that it's natural because, well, one thing is the homology of the reg space, and the other thing is just the pi1 of this reg space. So it's natural to suppose that it shouldn't contain more information. But here it's a very simple example where you see that it can contain strictly less information. And now the rest of my talk will be devoted to an outline of proof of this result. And the point is to show that this outline, well, is pretty generic, so that we can really have some hope to adapt it to some other types of regs, which is actually our dream with Marcus. And that is why I'm also presenting it to you. Maybe some of you will get interested in this method and be able to adapt it to other types of regs. So how does it work? As a first step, we need in homotopy theory, what you actually look at are the resolutions by some free objects. So you need to have a very good understanding of the free objects. Now, what would be a free permutation rank? So the only algebraic information you have on a permutation rank is the permutation itself. And the permutation is just the action of the group of integers, where the element 1 is acting by your permutation phi. And so this action will be free if and only if all your orbits are infinite. So from this point of view, it's easy to understand what free permutation ranks are. And then we need to understand the homology of these free permutation ranks in order to be able to put them into the machinery. So this we had to do explicitly. We didn't find any homotypical way to do it. And I will just show a very, very elementary but kind of funny idea which we used. So if you will start from the definition of a homology, it's, well, you take the kernel and you mod out the image. So you usually need to understand the cycles and then try to mod out the boundaries. So this is a natural way to compute things. But here we did things the other way around. First, we understood things for chain up to boundaries. So first we understood the quotient, and then we restricted ourselves to cycles. And so what this part means concretely, we showed that if you have some chain in your complex, then up to boundaries, you can replace this chain by a linear combination of things which start with the preferred elements of each orbit. So in each orbit you choose a special element, and you can make things up start from these preferred elements only up to boundaries. And then if you look, if you work only with these special linear combinations, it's quite easy to understand who will be the cycles. Now so the second step is the following. It's the usual step when you're working with a homotopy. So you take your object and you consider its simplicial resolution by free permutations. The good thing is that you don't need to know anything about this free resolution. You just need to know that it exists, and it exists from the abstract consideration, for example, from the interpretation of your Rank homology as equivalent homology, for example, or something of this type. So you don't really need to understand how these free permutations look like. And whenever you have this simplicial resolution, you can have a double complex by applying the Rank chain complex construction on each level. And if you have a double complex, you have two spectral sequences which have the same target. The first spectral sequence will start by looking at this direction, at the direction of the resolution. This is something very easy to work with. You'll quickly understand that starting from the second page, you'll have non-trivial elements only in the first column, and they will contain precisely the Rank homologies of your Rank. It comes precisely from the fact that you have a resolution, a free resolution here. So this is an easy thing. The second spectral sequence is slightly more complicated, and in computing it, you will need the homology computations for the free permutation ranks, which we were talking about in the previous slide. And using our computations and particularly expressing it in a more functorial way. I gave you just the Betti numbers, but you can express it in a more combinatorial way. You'll see that this on the second page, you'll have an expression which depends on the homology and on the reduced homology of one topological space. this topological space is what is called the homotopy orbit space. And this is the space I talked about in the very beginning. So you can take it from the map, you can build it from the mapping cone of your map phi, or concretely you can take some points, 1 point for each element of your set, and you need to relate by an arrow each an element A and an element phi of A. And so when you think about the space, you understand it immediately. Each finite orbit will give you a circle because, well, this chain will close, and each infinite orbit will give you a line, a topological line. So you'll have non-trivial stuff only in the zeros and in the first homology. And while putting it in this formula, you can make your computations. So you completely understand the second page. Now the remaining, the last step will be to identify, to prove that starting from the second page, this spectral sequence stabilizes. It will show you that these rec homologies, which you get from the first spectral sequence, can be computed by these very concrete homologies of these topological spaces, which you get from the second sequence. And if you work with this second spectral sequence, this formula will give you precisely the concrete formula from the previous slide. And how can you do? How can you show that this sequence stabilizes? So this is the thing which is really proper to our concrete computations. Well, you see that here you'll have only 3 abelian groups, and if at some point you have some non-trivial differential, then the Betti numbers will strictly diminish. And to show that this does not happen, you show that in the limit, which is the rec homology, you have enough linearly independent elements. We just explicitly constructed enough linearly independent elements to show that starting from this thing, you cannot have the dimensions diminishing. So that's the last point. And the whole, so the advantage of this construction is that a lot of things come for free. For example, step 2 comes for free. The first spectral sequence, the computations come for free. So you really need, if you want to apply the same ideas to another class of Raxi quandles, well, you need to understand what would be the free objects, make explicit computations for the free objects, and then here, look what you get on the second page from this understanding of free objects, and try to see if you stabilize or not starting from it by looking for many independent elements in the limit. So all the things really look reasonably doable, and our great hope would be that these techniques will be applied for other types of Rec and quandles. That's everything I wanted to say. Thank you very much.
Well, thank you.
And yeah. I'm very sorry I wasn't following the conversations at all.
Are there any questions? You'll need to unmute yourself if you have a question.
So I have written a couple of questions on the chat line. So I can read them aloud. Well, I was asking whether rec homology can do something in the case when we have a structure. I mean, for example, Legendrian or transverse nodes. And Scott answered my questions partially, but Victoria, you can read so what was written there.
Yeah, so Scott gave the answer. In general, there is a close, if you have a quandle, there is a close connection between the rec and the quandle homologies. So the quandle homology will be, the rec homology will split in 2 parts, the quandle one and the degenerate one. And the degenerate one can be understood using a spectral sequence constructed by Joseph Przyczicki and Krzysztof Butyra. So these things are understood. So they are computing the two are more or less equivalent things. And now, what you mean substantially simpler? Well, the formulas are already quite simple, and so the second part of your question, I don't know whether having some additional structure like Legendrian structure can hand in the fundamental quandle. So I have never seen works going in that direction, but it's a good question. Maybe there is something to look up, to look into. And your last question: is there any chance to present quantum homology as is index in the RTA single sense? I'm not aware of it. I'm not aware of any work trying to mix the two things, the quantum homology and the index theory. So it's another nice question to look into, and as far as I know, it's completely unexplored.
Sounds like a good topic to look at, I think. Yeah. Are there any more questions? Well, I'd like to thank Victoria for an interesting, stimulating talk.
Thank you all for listening.
Can I just say about next week, which is the last talk this term, and it's at the usual time of 5 p.m. GMT, and it'll be given by Rob Kirby of Berkeley.
Does he have a title?
No, he hasn't sent me a title yet. He's still trying to wrestle with the the technique of Zoom, but I think he'd probably got it by now.
It'll undoubtedly be about trisections.
Yes, I think, I think I heard that. Yeah.
What did you say? Say that again.
I said it will be about trisections of four manifolds.
Oh, right. Yes. Of course. Yes, it will be. You're right.
Okay, well, many thanks to everyone for being here and Victoria for the talk, and hopefully see you next week. Bye for now.
Bye, Rog.
Goodbye. Thank you.
Thank you.